Now let's look at the RT configuration. As you can see, there's 4 settings you can choose from. Default settings, read from a folder, read from an RD file, or a read initial settings from RT. The default settings. To use the default settings, select this radio button. The following pages will contain the default settings that the RT was delivered with. Read from a folder. It is possible to store configurations in a folder. The configurations require several files, so it is tidier to keep it in a folder by itself. To read the configuration from the folder, select this radio button. A group button will appear and the folder can be selected. Read from the RD file. The RD file is stored within the RT. The file contains the configuration used when the RT was running. To load the configuration from an RD file, use this option. Read from the initial settings of the RT. If the RT is connected to the computer via the Ethernet, then it's possible to read the initial settings directly from the RT. The initial settings are the settings that the RT starts up with before it makes any improvements. Select this radio button and enter the correct IP address of your RT. Now let's look at the RT configuration orientation. The RT can be mounted at any angle in the vehicle. The output can be rotated so that the measurement can be referenced to the vehicle's coordinate frame. For correct initialization, it is also necessary to get the heading orientation correct. If the vehicle level option is used, then the pitch and roll orientation must also be correct. The RT gets its initial heading by assuming that the RT velocity or slip angle is small. If the definition of the vehicle x-axis is incorrect in the RT, then it will not initialize correctly when the vehicle drives forward. The orientation of the RT in the vehicle is normally specified using 3 consecutive rotations that rotates the RT to the vehicle's coordinate frame. To make it simple to configure the RT's orientation in the vehicle, the RT config asks the user to define directions that Y and Z axis points in the vehicle based on the diagram shown. To make small adjustments, use the advanced settings. This allows the user to zero any slip angle offsets, pitch offsets, or roll offset. Now let's look at the RT configuration. The primary antenna position. It is necessary to tell the RT the distance from the measurement point to the GPS antenna measurement point. This should be entered in the vehicle's coordinates frame. The accuracy of the measurement should also be specified. Care should be taken here because it is very easy to measure distance to 1 meter or better in a straight line. It is much harder to measure to 1 centimeter through a car roof, and it is much harder to measure to 1 centimeter if the RT is slightly misaligned in the vehicle. Telling the RT that you have measured the distance to 1 millimeter may lead the RT to believe its results are better than they really are. You may be impressed by the accuracy that the RT reports, but in reality it will not be as accurate. The RT configuration. Secondary antenna orientation. If the system has 2 antennas, then it is necessary to tell the RT the orientation of the 2 antenna system compared to the vehicle. It is critical to tell the RT the exact distance between the 2 antennas. It is best to mount the 2 antennas on the top of the vehicle, although it is possible to mount one on the roof and one on the bonnet or hood. In reality, the multipath reflections from the window screen will degrade the performance of the system. Getting the angle wrong by more than 3 degrees can lead the RT to lock onto the wrong heading solution. The performance will degrade or be erratic if this happens. The RT does not estimate the distance between the two antennas. It is essential to get this right yourself, otherwise the system will not work correctly and the performance will be erratic. A new feature called Enable Static Initialization can be used to initialize the system and determine position and heading without leaving stationary position. This will avoid the chance of incorrect heading being set for some reason, e.g. reversing out of a space before the system has initialized and getting heading lock in the wrong direction. Now let's look at the RT configuration options. This is very important when it comes to understanding how the software works and to make sure that your system, the RT system, is getting the correct data for you. It is a very good idea that you go through these options while testing the system practically. This way you can see the effects on different options will have on the system, and their relevance will become clear much faster. Vehicle starts. If you know that the vehicle will be level when starting to within 5 degrees, then the level option can be used. This saves about 40 seconds during the initialization process, since the RT does not have to take the time to compute the initial roll and the initial pitch. In the high vibration environments, the not level option may not work, and so the RT can only start if the vehicle is level and the level option has been specified. Vibration. The normal vibration levels is adequate for most circumstances. The RT is very tolerant of vibration and has been used successfully in environments with more than 2G RMS using the normal setting. If the velocity innovations are very high and many GPS packets are being dropped, then this setting can be changed. GPS environment. If the system is used predominantly in an open sky, then the open sky setting should be used. In environments with a lot of GPS multipath, the other two settings can be used. This will allow less accuracy GPS measurements to update the system. Differential. The RT can be configured to use several different differential correction message types on connector J3. The RT base transmits RTCA messages. The RTCM or CMR can also be selected, or the port can be disabled. The advanced option should not be used except in specialized applications or circumstances. SBAS. For SBAS enabled systems, the GPS receiver can be set up to receive corrections in North America or Europe. Because WAS or EGNOS are in test mode, they can sometimes be unreliable. The corrections can be disabled by selecting None. For systems that do not have SBAS capability, this setting has no effect or is ignored. OmniStar. For OmniStar enabled systems, the correct satellite should be selected for the region where you are operating in. The correct satellite must be selected before OmniStar can send a new license. For systems that do not have OmniStar capability, this setting has no effect and is ignored. OmniStar satellite use requires a fee to use. Now let's look at the RT configuration for the advanced slip. The advanced slip feature uses characteristics of land vehicle motion to improve heading and slip angle. This feature must be disabled for airborne and marine systems, where the lateral velocity can be significant. The advanced slip feature applies heading correction when the land vehicle is not slipping. When the car is slipping, the lateral acceleration is usually large enough so that the normal heading corrections provide excellent results. For the advanced slip feature to work correctly, the system needs to know the position of the rear wheels on the vehicle with front wheel steering. Minor steering of the rear wheels does not significantly affect the results. A position of the road height midway between the rear wheels should be. The advanced slip feature also requires some knowledge of the road surface. Three predefined options are given: normal, low friction, i.e. ice, high friction. The other feature should not be used. Now let's look at the examples of the RT Advanced Slip. In this example of a step steer test is shown. The data has been processed both without and with advanced slip. It can be seen that the slip angle at the end of the test is the same in both cases. The slip angle is different at the start of the test. The top graph, without advanced slip, has about 0.4 degrees of heading drift at the start of the test. During the straight run to the test, the heading has drifted. At the end of the test, the acceleration of this test has enabled the Kalman filter to correct the heading of the drift. The bottom graph, with advanced slip, has a much smaller heading difference between the start and the end of the test, about 0.1 degrees. Here the advanced slip is operating correctly during the straight lead-in to the test, and the heading is kept accurate. During the test, the advanced slip turns off automatically to prevent real slip angles from upsetting the heading. Now let's look at some more options for the RT configuration. The CAN. The CAN bus can be disabled, or the correct baud rate can be selected. In systems without the CAN option, this should be set to disabled. Heading lock. The heading of a single antenna system can drift when the RT remains stationary for a long period of time. To solve this, the RT includes an option to lock the heading to a fixed value when stationary. This option can be used if the vehicle can turn on the spot, i.e. turn with 0 speed. With heading lock enabled, the RT can remain stationary for an indefinite period of time without any problems. For vehicles testing, this option is recommended. Garage mode. The garage mode option can be used to stabilize the RT outputs when GPS is not available. For example, GPS can be blocked when the vehicle returns to the garage to have some modifications. Without garage mode, the RT may drift too far and may not be able to recover. When the garage mode is active, the RT applies a gentle velocity update and assumes that the vehicle is stationary. This keeps the roll, pitch and velocity within acceptable limits while the RT has no GPS. With heading lock also enabled, the RT can also keep the heading accurate while stationary. Initialization speed. This is the speed at which the system will engage and attempt to making position and heading lock. The default starting speed for the RT is 5 meters per second. However, some slow vehicles cannot achieve this speed. For these vehicles, adjust the initialization speed to a different value. If a speed less than 5 meters per second is selected, then care should be taken to make sure that the RT is traveling straight when it is initialized. Avoid reversing above this speed before the system is initialized, or the heading will be locked in the wrong direction. Displace output. The RT can displace or move its outputs to another location in the vehicle. This simulates the RT being mounted at a new location rather at its actual location. To enable output displacement, select this option and enter the offsets to the new location in the vehicle. Analog outputs. The channels for the RT ANA are configured in the RT. Up to 16 channels can be selected from about 40 different output options. Use this setting to choose the analog outputs. Angular acceleration filter. The RT measures angular acceleration. When driving in the vehicles, the vibration causes the angular acceleration to be very noisy. The RT can filter the angular acceleration to reduce the high frequency noise. Several filters can be specified as well as a cutoff frequency. Only angular acceleration outputs are filtered, none of the others. Wheel speed. The wheel speed input is used in survey applications to reduce drift when the GPS is not available. For example, when the vehicle goes under a bridge, it will predict a position over time based on the wheel speed. Local coordinates. The local coordinates option allows the user to configure the base latitude and the base longitude. These are the positions on the test track where the X position and the Y position are 0. A rotation for the local coordinates can also be specified. Serial 1 output. Choose a data type to output over the serial 1 port and the baud rate. Ethernet output. Select the data output packet and the data rate. The output of the data can be automatically triggered. If multiple RTs are transmitting data, the output can be delayed to avoid packet loss over the LAN. Steering robot IP. If you're using an ABD steering robot, the IP address of the robot should be entered here so the RT software can communicate with the robot on the LAN. Output smoothing. The error correction in the RT is always smoothed, usually using the first order filter. However, for some applications, even more smoothing is required. These are very advanced settings and should only be used or modified with the advice from Oxford Technical Solutions. Slip points. The RT can output the slip measurements for additional points, a maximum of 8 points. On the canvas, select the number of slip points using the General tab, and each slip points tab shows the measurements from the RT to the slip point. GPS control contains advanced options relating to the GPS algorithms that merges the GPS and the inertial data in the Kalman filter. The user can choose between the GPS card standard settings or Loan's IX/GX algorithms. Surface tilt. Used to compute roll pitch and heading compared to a flat inclined surface. Enter the heading compared to true north of the uphill direction and the gradient on the surface. Altitude. The RT can output altitude compared to the WGS84 ellipsoid compared to the geoid, or a constant offset compared to the WGS84. By default, the RT outputs altitude compared to the geoid. On the RT3000 or the RT4000 products, the EGM96 geoid is used. Advanced can be used to manually enter commands to be sent to the RT in the configuration file. These commands have a wide range of functions and will be provided by OxTS on request from support@oxts.com. Now let's look at the RT configuration committing. The changes to the RT setting must be performed using the Ethernet. It is necessary to configure your computer Ethernet settings so it is on the same network as the RT. Refer to the Ethernet configure earlier in the course of details. Enter the IP address of the RT that you want to configure. The IP address is usually 195.0.0.x. The X is the serial number of the RT. The changes to the configuration do not take effect until after the RT is reset or the next power on. Press Commit to save the configuration on the RT. The RT will reset automatically loading the new config. Now let's look at the RT configuration, keeping a local copy. Before finishing, it is possible to save a copy of the settings in a folder on your computer. This then can be reloaded the next time. The finish screen also lets you know if the settings have been committed successfully to the RT or not. To save a copy of the settings to a local folder, check to preserve these settings in a folder checkbox and enter the folder name. Now let's look at the CAN DBC files. One CAN DBC file is provided. The rt3k full.dbc file includes all the status messages.